Okay, sweet. All right, so welcome to this week's tutorial on TensorFlow. So the goal of this tutorial is to give people who have never used TensorFlow a short introduction on what are the core principles behind it, and how to use it for doing things that are not necessarily machine learning related. So the example that we designed with Zachary is an example of how you use TensorFlow for doing classical MRI reconstruction. So the idea is that we want to show you that it's not just a deep learning framework, it's very powerful and you can use it for a bunch of things. So in order to access the tutorial materials, you can get, as we already showed, you can go to the GitHub CosmoStat tutorial page, and then you have direct links to the notebooks that we're going to show you today. So we have two notebooks. The first one will be an introduction to TensorFlow, and the second one will be an example of how to use it for doing this MRI reconstruction step. So the way we recommend you to follow along today is that you click on this button. It will start a Google Collaboratory notebook for you. There you go. And okay, so my phone is, sorry, responding to my saying the word Google. And you can just put this window next to the Zoom meeting so that you can follow along on your notebook. All right, so before we go through this first notebook, one quick thing to show you if you've never used Google Collaboratory before. On the left, you have access to the table of content for the notebook with all the main sections. One important thing to know about also is that you can choose what type of runtime you want to use. So this notebook will be executed in the cloud. And by default, it doesn't use any hardware acceleration. But so it doesn't matter for this one, but for the next one where we'll be doing some GPU stuff, you can choose GPU here. And it will actually make sure that your notebook is run on a cloud node with access to GPU, and all of the code that use TensorFlow will actually run through a GPU. All right, so that's a good thing to know. And now let's look at what we'll cover here. So the goal of this tutorial is to give you a quick introduction of what are the core principles of TensorFlow. Feel free to interrupt at any point, ask us questions, because the point here is for you to understand things. And if there's anything that seems not clear, just let us know. All right, so we'll go over basic ideas. And then the very important thing that TensorFlow allows you to do is to easily compute the gradients. And we'll see what that is and how you can use it. And we'll show a very short example of how you do optimization with TensorFlow. All right, any questions at this point before we dive in? Can everybody load the, so I can't see your faces, but if you have any issues with loading the notebook, just let us know. All right, I'm going to assume that everybody is set up, so let's start. So the first thing that we want to cover is what is tensor. So TensorFlow is based on this concept of tensors. You can think of them as essentially some sort of array that is defined by a given shape and a given type. So here is a very minimal code where we import NumPy and we import TensorFlow. And here we define our first tensor. We initialize it to be 0 and with a given shape. You can go ahead and execute this code. And on the next line, you will see you can just press enter and you will see what this type of object is, what this object is. So you see here that X is a TensorFlow tensor. It gives you also the shape of X. So it's like size 8, which is what we specified here. Type float 32. So that means it's a single precision float, and that's the default for all TensorFlow tensors. And you also have access to something that says NumPy with an array. So that shows you what is the value of that tensor. can execute it here. Right. And that's all there is to it. So a tensor is just an array with the shape and the type, and you can get access to the value of the tensors through this NumPy property. So here's an example of how to go back and forth between plain NumPy array and the TensorFlow tensor. So here we define a NumPy array. So this is pure NumPy Python code. And here we use this TensorFlow TF convert to tensor function that turns your NumPy array into a TensorFlow tensor. So I can evaluate it. I see that A here is a TensorFlow tensor. I can also look at X, and X is just a NumPy array. All right, so that's how I turn any NumPy array that I have into a TensorFlow tensor. But I may want to do the inverse. I may have access to a tensor, so for instance, A, and I want to retrieve the value in terms of a NumPy array. And I can do this by using the .numpy function on that tensor. So A is a tensor here. I do .numpy, and I retrieve my NumPy value. All right, any questions about this?
I guess the advantage then of having a tensor rather than the just NumPy array is just for convenience for how TensorFlow works. Right?
So they are not the same thing. So the NumPy array is stored on your CPU. I mean on your main machine RAM. The TensorFlow tensor is actually a symbolic representation of something that happens on the GPU. So when I do this here, this is a CPU array. And at this point, A is actually something that is stored on the GPU. And it's on the GPU, and it will be used through, we'll see in the next section, how these tensors are combined together for forming computations on the GPU. So here you see the same kind of data, but actually they are not the same. They are in different places, different types of objects.
Sorry, yeah. What happens if you don't have a GPU?
It will also happen on CPU, but when it's a tensor, it's being managed by the TensorFlow runtime, and it's a different beast than NumPy objects. So the tensor here, you don't really actually know where it is being stored, but if there is a GPU accessible, it will automatically be allocated on GPU, and it will be used on the GPU for doing operations.
And where is the X, the NumPy array stored instead?
So here it's normal Python memory on the CPU. At this point, here A is a tensor that may run on CPU or GPU, depending if you have a backend for computing. All right. So NumPy arrays cannot be used for further TensorFlow operations that we'll see after. And so they first need to be converted into tensors, and then tensors can be manipulated in all sorts of ways by TensorFlow. All right, so maybe it will get clearer at the next section. So here is just to show you that you can go back and forth between the two. All right, so now we have this notion of tensors. So tensors are things that, let's think of them as arrays. But in TensorFlow, you have also the second term, the flow part. So what's up with that? So in TensorFlow, a computation, so a program, you can think of it as a series of operations, ops, that are being combined together into a computational graph. So a computational graph is something that looks like this. You have tensors, A, X, and B here are tensors. And they are combined together by some ops. So multiply and add here are ops. And all of them together, they define a computation through a graph structure like this. So let's say I want to compute something like y equal ax plus b. I can turn it into a computational graph that will look like this, where a, x, and b, and y are actually tensors. So they represent states in the computation. And they are being combined together with very simple ops. So multiply takes just the a and x and returns a new tensor that is just a multiplication of the two. And add is the same thing, but with additions. All right, any questions here? So the idea is instead of just like if you were to write this as a NumPy operation, NumPy will just run the operation and return the results. But here, TensorFlow keeps track of the actual computational graph and the entire track that leads to a result y. And we'll see that this is super important afterwards. All right, so let's see how we would define such a thing in TensorFlow. We introduce these tensor A, B, and X. So let's say A is just a tensor full of ones, zeros, and then we allocate a new tensor X this way. And here is how we define the computation. So under the hood, what happens here is that TensorFlow knows that because these things are tensor A, X, and B, it knows that when we type that, it takes the tensors together, it combines them with this TensorFlow up, and it returns the result. Then it combines the results of that with the next up here. And at the end, if I run this, what I have access to is this tensor y that represents the end of the computation. Any questions here? All right, so here, when I type y, I get directly the results. So I can do here, I can change my factor. I can do 2 times, boom. And now the value will be 2 times the input. And this happens automatically and quickly because we're in TensorFlow 2 where computations are directly evaluated. So one thing that is also important to know in TensorFlow 2 is that instead of writing things down this way, where here it will evaluate this up and then return the results and then combine the results with this thing and get the full result at the end, you can combine a bunch of TensorFlow ups together inside a function. And that function will actually be the complete representation of this graph and can be combined together into something that runs on the GPU. So here is the same operations, right? Just written down as a NumPy operation. So I can run it and I get a result. So this is pure NumPy code. And I can turn this pure NumPy code into just the same thing, but in TensorFlow using this at TensorFlow function. So what it does here is that TensorFlow will understand that this function takes 3 inputs and returns the result. And any ops that occur inside this function will be put together into a same computational graph. And when I evaluate this function, what it does is that it takes the inputs. If they are not already tensors, they are converted in tensors. Then it sends those inputs on the GPU. The entire function is evaluated on the GPU. It doesn't come back to the CPU. It doesn't come back to Python. And just at the end, it grabs the results and it returns it to Python. So here it's a very simple example, but we see that the result of this function is a TensorFlow array, despite the fact that we did not put any tensors at input. They were automatically converted in tensors. So here it's a very stupid operations, but if we had much more complicated functions with, let's say, Fourier transforms and everything like that, they can take time. But if you put them all together inside the TensorFlow function, it gets all evaluated as one block on the GPU. So it's a nice trick to remember. Any questions on this?
I have a question. When is it possible with TensorFlow to get access to simple information like the mean and the max or the average, like with NumPy array?
Yes.
And if you call a NumPy function on a TensorFlow array, does it work and where does it run?
I can do well, okay, this is stupid. So let's go back to this example here. Y is already a NumPy tensor, sorry, a TensorFlow tensor. I can do np.sum of y. This should work. And it gives me 20. And why does it work? Is because the API is kind of the same between NumPy and TensorFlow. So the NumPy function calls the like knows how to manipulate things that behaves exactly like an NumPy array. Some functions may not work exactly that way. So you can, in any case, turn your tensor into a NumPy array and then use your NumPy functions like this. Does that answer your question?
Yeah, so I guess here it's using the classical Python interface. It's not,
Right.
doesn't have anything to do with TensorFlow.
Right. So I can do the same operation in TensorFlow using a TensorFlow operation. This is a TensorFlow up that is going to compute the sum of all the values in Y. And we'll see that the difference is that I get the same answer, but now the answer is an actual tensor, which can be manipulated through additional ops afterwards.
Okay, and what if the function that I want to use is not implemented in TensorFlow? Do I have to write a wrapper like you've done with like the at TensorFlow function, or?
So you can, if you have a complex function, you can write it down in terms of simpler operations this way. But there are already a ton of things that are already implemented in TensorFlow. Okay. So just look through the TensorFlow API for the function you want, and unless you want something very, very strange, it should already exist.
Okay.
And how do I find the list of APIs which are available?
Right. So that's the, I'm going to show you, it's because it can be useful. It's right at the end of the notebook. You have the documentation with all of the functions. You also have a search bar over here, so you can search for the thing that you want, and you will find it. All right. Okay. So that's a computational graph, how you can define one and execute one. So it's super simple. And now, why do we care so much about this graph representation? It's because of the next point that we wanted to tell you about the fact that you can use TensorFlow to automatically compute gradients through automatic differentiation. So if you don't know already what this is super important when you want to train neural network. So neural network is actually, you can think of it as a very complex graph of operations, and you want to optimize some parameters of that graph. And so if you wanted to compute the gradients of the loss function with respect to those parameters manually, it would take forever. It would be a nightmare. And instead, because TensorFlow knows how to introspect the computational graph, it can compute gradients automatically by applying the chain rule. So here is an example of how that works. Let's come back to the same operation that we had before, y equal ax plus b. We can split it into simple ops, this thing. So that's what TensorFlow does under the hood. It first computes a times x and stores it as a tensor u, and then does u plus b to get the answer y. So now if I want to compute the derivative of y with respect to x, I can use the chain rule and split it into individual derivatives for those individual operations. And so TensorFlow knows what are those derivatives for simple ups. And because when you have a complex graph, it's just a combination of simple ups, you can compute any gradients you want in your graph by just a concatenation of simple gradients. So if you apply the chain rule on this operation here, you end up that the derivative of y given x is a, just by looking at those individual ups. So super easy. Any questions here on the premise? Right. So let's see how you do the same thing with TensorFlow. So let's set up a problem that is a classical problem that you usually have. So I'm going to set up an operator that I'm going to call A. I'm building it to be a random matrix, and then I play a little bit with this matrix to make it orthogonal. Doesn't matter too much. It's a linear operator, so it's a 64 by 64 matrix. Oops. Then I'm gonna create an input vector of size 64. I'm calling it x true. It's gonna be just zeros and 2 ones in this vector. Then I compute y by doing a time dot x. So it's a matrix multiplication Here it's all NumPy code. There's no TensorFlow here. This is something that you see happening every time when you have a linear problem. So here is what this looks like. This is my matrix A. This is my input signal X, and that's let's say some measurements that I would get if I do y equal AX. Any questions here? Okay, so if I want to solve this problem of given some measurements, what is the true signal X? I want to, for instance, minimize the difference between the measurement and some forward model of X through my operation A. So I want to guess the X that minimizes this loss function, right? So this is something that we do every day when we do compressed sensing or this type of things. So if I want to optimize the value of X, what I actually want to do is to compute the gradients of this loss function with respect to X, and then do gradient descent by updating X according to those gradients. So if I do this classically, I would have to manually compute what is the derivative of this function with respect to X. So this is a simple one, and I know how to do this. So I know that the gradient will look like this. And so the classical way of doing optimization on this type of problem is that you would define a function that computes the loss, and you would have to define a separate function that computes the gradient. And you can only do this when you have actually worked through the math and figured out what the gradient can be. If any of you has done this in real life at some point, you know that it's in principle simple, but sometimes it can get very tricky, and getting the gradient is not always easy. But here it's kind of easy. So let me execute this, and let's see. Oops, I forgot to execute this one. Right. So here what I do is that I take a first guess for what my solution of my problem might be. I compute the loss for this guess, and I also compute the gradient for that guess. Which means by what amount I should update X in order to reduce my loss. So here is what it looks like. The blue are simulated measurement Y that we want to fit. The orange is our first guess solution here. And what we see here on the right is in purple is the gradient that we should apply to X in order to recover the solution, or to go towards recovering the right solution. Any questions here? All right. So now let's do the same thing, but with TensorFlow. So if we know that TensorFlow can compute gradients, we hope that we don't have to write down the gradients manually. So we'll define a TensorFlow function that computes the loss. So it's almost exactly the same thing at the previous function in Python that we had, but now I'm using some TensorFlow operations. So for instance, the sum, instead of doing NumPy, I turn it into TensorFlow reduce sum. It's the same operations, but with TensorFlow. And here I do a matrix vector product, but it's the same thing. So that's my reconstruction loss, if you want. And then I'm going to create a TensorFlow tensor out of my first guess value that I had created before, but it was in NumPy. So now everything after this function will be TensorFlow operations. Right.
And
so,
one question, Francois.
Yeah.
I thought the decorator would automatically convert everything into tensor. So why are you using, or do you need to use this TF functions inside this?
I need to have to manipulate it here because I'm going to need it over here. It needs to be a tensor at this point.
No, but I mean inside the loss function.
Yeah, inside the loss function,
Can you use the
I don't
same as
need to.
before, just with the decorator?
Yeah, same as before. It will be converted as a tensor, but we'll see that in the next cell, I actually need to have a handle on tensors directly, not NumPy arrays. So I convert it beforehand.
Okay.
And we'll see why. So that's a good point. All right. So now that I have my loss function, the thing that I want to do is compute the gradient of my loss function with respect to the input X. So in TensorFlow 2, the way to do this is through this thing called a gradient tape. So gradient tape is a tape, like a recording tape, that is going to record the execution of the TensorFlow graph. So it will actually store all of the ups that appear in your graph. and it will keep them in mind so that then it can go back, look at the graph, and figure out what are the gradients of whatever tensors you want with respect to whatever other tensor. So the way you use it is this way. You open this context by saying with TensorFlow gradient tape as G. Within this context, any operations, any TensorFlow operations that are being executed will be recorded on this gradient tape. So one thing that I do here is that I tell TensorFlow, keep an eye on this tensor XTF that I've defined before, because I will want to know afterwards what are the gradients of the loss with respect to this tensor. So I need to tell it to keep an eye on it through the operations, during the TensorFlow operations. So I just say, watch this tensor, because it would be important afterwards. And then here I apply my TensorFlow loss function that I've defined over there. So it takes my tensor as an input. It takes y and a. So y and a here are actually still NumPy arrays, but they will be converted into tensors automatically. Right. So this is TensorFlow code. All right. And that is all I need to do here. So now I want to ask TensorFlow, what is the gradient of my loss with respect to my input tensor XTF? So the way I do this, I interrogate the gradient tape. I take the tape and I do dot gradient of the output given some inputs. So I say, give me the gradient of the loss with respect to the input tensor XTF. And that returns a new tensor that stores the gradients. So let me execute it. I'm not sure I run everything. Boop, boop, boop. Right. So what we see here is that the loss that we computed in NumPy before is exactly the same as the one that we get with TensorFlow. That's good. But we can also look at the gradients. And what you see here in blue are the gradients that we computed analytically through our use of mathematics, which is so 2010. And in orange is the one that is automatically outputted by TensorFlow. Any questions here? Because this is essentially all there is to it.
So in practice, you mean that in the TensorFlow representation, even, I mean, we can calculate numerically the gradient without knowing explicitly or coding explicitly the analytical form as you did in the
Exactly. So all you need to do is write down the forward model. So here I just define my loss function. If I had very complicated loss functions with many layers of operators and everything, it would be a nightmare to try to compute the gradients by mathematics. But here, TensorFlow actually knows how to introspect that computation graph and figure out what should be the gradient, and does this automatically for you.
And if one of these operations, it's let's say a numerical thing, like I don't know, some NumPy integral, or some even coming from another, let's say, code or whatever, or even like reading some input, is it possible? Or
so
which kind of operations are possible?
So the gradients will only work with out of the box if you use TensorFlow ops. If your computation goes through something that is not a TensorFlow operation, then you're lost, because that operation needs to define a gradient. So let's say that you have a complex computation, but you know analytically what should be the gradient of that computation. You can define your own specialized TensorFlow op that implements both the forward pass and the gradient with respect to the input. That's advanced TensorFlow. I don't want to talk about it here. So it's possible to wrap some existing code as a TensorFlow op as long as you know how to define the gradient of that code.
And in terms of computational time, is there one that is better than the other?
TensorFlow is better.
Okay.
It goes on, if you have a GPU, it goes on your GPU.
So even if you know analytically the gradients, TensorFlow is still faster.
It does. So what it does, it figures out, it introspects the code, and it figures out that the expression of the gradient is this, and then it runs this.
Okay, so it's still analytical.
It's yeah,
Kind of.
It knows how to combine the right building blocks, and it executes it exactly the same as if I had written it done myself.
Okay.
All right.
And
so
how is it actually calculating? How is it actually calculating? What calculation is it actually doing? And I mean, I imagine that there is some way to tune the precision, for example, of for more complex functions.
So what it does is exactly this. It looks at the forward graph, right? It splits it into single operations. And for each of those operations, TensorFlow knows what is the TensorFlow representation of this gradient. And then it creates a new graph, putting together all of these ups together, and then it executes it and gets the result. So it knows, essentially it knows how to do derivatives, symbolic derivatives, and then it executes those derivatives because it figures out what is the expression of this derivative. So in this case, it actually figures out that the gradient has this form, and it implements it as a graph and it runs it. So it's not.
François, I just have one question
Sure.
for this. Is let's say that the graph is actually simplifiable into a smaller graph. TensorFlow, I think, so if I'm correct, TensorFlow doesn't do the simplifications itself, right?
No, I don't think so.
So there might be cases that Axel was talking about where you have something very complex, which actually stands for where the gradient is actually very, very simple, just because you can do some computations that are not inherent in the chain rule. And then in this particular case, implementing the gradient yourself would be faster computationally speaking.
Yeah, that's a good point. Yeah.
Okay.
Yeah. So you can beat TensorFlow if you know that the gradient should be 1 or something. You can beat it. But in the general case, that's not the case. So it's only in specialized cases, I'd say.
Is there any parameter that we can, I mean, tune or fix that we have to choose that change the precision that, for example, of the step that he's taking in calculating this gradient? Or
so there's no. So it's not a Fisher thing. It doesn't do differences. It figures out that the gradient of this loss is this computation in terms of matrix multiplications and which matrices need to be computed. So
this is only because right now the function cannot be expressed in that way, but for a more complex function for which
it's always the case. It never does numerical differences. It always figures out that if that's my forward computation, by applying the chain rules, it figures out that this is the computation for the gradient, and then it executes it numerically. So it just evaluates this function, but it doesn't try to compute the gradient by numeric finite differences.
And what happens if the loss function is not convex?
For instance? So that's not a problem, but if it's not differentiable, let's say an L1 loss, you forget about it. You pretend that it is, and you move on.
But it works?
Yeah.
And L0 it works as well?
No, because it's a little bit worse. We'll see this in the second part where Zachary is going to show you an example of an L1. Okay, so that's the basics. The last thing that I wanted to show you is how to do optimization. So now that we know how to compute the gradient of a loss function, we can try to do gradient descent, right? So in this case, we'll need to update our estimate for x. And so instead of just using a regular tensor, we'll introduce the notion of variable. So variable, it's kind of like a tensor, but it also has a specific value that is set, is always the same. And you can update that value by assigning a new value to that variable. So here is how you create a new variable. So this will be where I keep the solution for my problem. I initialize it to 0, and I say that it's trainable, so that when I use optimizers, they know that they should update this variable if it needs to be. So now I can do the same thing as before. I can compute the gradient of my loss with respect to this variable. And you note here that I don't have to tell TensorFlow to keep an eye on this thing, because it's a variable, and by default, it will keep eye of all the variables, because it expects that you will then ask the gradients with respect to the variables. So I compute my loss with the variable as an input. I take the gradient, and I do one step of gradient descent. I take my variable, I assign a new value by doing subtraction. So it's just doing x minus this thing. And I can look at the solution, and boom, I get the right answer. So here I get the right answer by just doing one step of gradient descent, because I cheated and I have a matrix A that is orthogonal. And so one step of gradient descent is all you need. In practice, you would need more steps. Any questions here?
What does trainable mean?
So here we are doing gradient descent by hand. So we compute the gradient, and then we assign, we update the value of the variable. What we'll see just after that is that this is tedious. And when you have a very complex model, so for instance, a deep neural network, you have thousands and thousands, hundreds of thousands of variables. So you don't want to have to manually assign new values to all of them. So you just say this variable is trainable, and then you will use what's called a TensorFlow optimizer, which will actually just do all of this for you, and it will update all the variables that you've said are trainable. Otherwise, it will not train them. So just to tell the optimizer, okay, you can update this value, or don't update this value because I want it to be a specific value.
Okay. On that, use a tensor with.
Sorry, I didn't get that.
When would you ever use a TensorFlow? I think I might be breaking up, sorry. A TensorFlow variable that's non-trainable instead of just a tensor with set to the value that you want to be set.
I can't think of a use case right now. So you can safely just let them trainable. It would need to be a complex thing that we're not going to cover today.
All right, thanks.
All right, so just to show you how.
Yeah. Question. What is assign sub in the?
Right. So assign. If you do assign on a variable, you just assign a new value. When you do assign sub, you say I want to update the value with a delta. So that's what is shown here. So you also have assign add. If you do assign add, it will add this delta to the existing value. If you do assign sub, it will subtract that delta to this already to the existing value. So this is equivalent to doing assign x var minus. Okay.
Okay. Yeah.
All right.
So, but if I understand, sorry, if I understand that basically this whole bit would be in practice the optimizer that you would choose when you compile a model, when you build up the neural network.
Right. So let's see right after that. So I'm going to skip over this part, which is how you write your own operation, because we'll see it again in the next part. But here is how you would use a TensorFlow optimizer to automate this entire thing. So now I define my variable again. I instantiate a new TensorFlow optimizer, and I tell it to optimize a function that takes no arguments. So here I'm using a Python lambda function, but it's just to define a function. And that returns the loss that you want to optimize. So the first argument of minimize is a function that returns the loss. And it takes as a second argument which variables you want to optimize over. So instead of having to compute ourselves the gradients and everything, I can just do this code. And under the hood, minimize is going to compute whatever gradients from the loss that I've provided in order to update these values and do the optimization. And so I can execute it. And here again, it finds the right answer in one step. So this is to show you the two ways to do things. Either you write your own fine-grained things where you compile, you get the gradients yourself, you optimize, you can do a loop to do several steps of optimization, or you use TensorFlow optimizers directly that do everything for you. All right, so this is all we wanted to say for this part. Any questions?
I have a question on this last part.
Yep.
How do you change the number of steps that you want to do for when it's fully automated?
Right, so here, this performs only one gradient descent operation. So if you want to do 10 steps, you would do this.
Okay, that's all.
So that that calls the minimize function 10 times and does that 10 steps of gradient descent. So this is a very stupid example. One is enough, but this is how you would do more.
And apparently for me, when I run it, one is not enough. I still have a noisy solution.
Oh yeah, because because here I've added noise. Actually, if you try, you'll see that whether you run one or several steps, you will get the same answer because we have a very specific operation here.
Okay.
All right. So
I have a question. Sorry. Yeah. How does it handles the non-differentiable losses?
It's so for the purist, this is unthinkable. But it just makes whatever is non-differentiable differentiable. So for instance, the N1 loss, the gradients at 0, it just says it's 0 and move on.
Okay, thanks.
Yeah. Okay. All right. So
yes, thank you. Sorry.
I hope this covers most of the things, and now I will release my screen and give the screen to Zachary, who can show you how to use this in practice.